All right, so people start to join the session. So we still have a few minutes before the TA session. And right now, if you have any questions, you can just feel free to ask. And I have to manually accept everyone to join. All right. So let's just get started and see what we are going to do today. So, so first of all, we will do some questions together, and then I will actually talk about some techniques when we do those questions. So the first question is about the demand function. So the demand function can be a function of a lot of variables. And first of all, it's a function of the price of the good, right? The quantity demanded is the function of the price of the good, of course, but it's also a function of, for example, income and the prices of other goods. So we usually just want to focus on the relationship between the quantity demanded of the good and the price of the good. Okay, so what we end up doing is to fix all the other variables. We call it ceteris paribus. So we just figure out what the values of other variables are, and then we plug those numbers into the demand function, and then we are left with just Q and P. So the first question is not really hard. So once you plug in the values of all the other variables, you're fixing all the other variables at their current values. And then you are left with the relationship between quantity demanded and the price of the good. So that's what the first question is about. So there's actually nothing really important to talk about. So we'll just skip that first question.
Hey.
All right.
Can we go back to that last part, sorry, where you got those constant values? Were those just given in the previous example?
Yeah, those will be given. Okay. So, or you will have to do some investigation to collect some data to actually see what those numbers are. But in any of the questions that you will see in this class, they will be given. So you don't need to do any calculation, just plug in the values. So I guess this is a very simple question. So the next question is slightly more complicated. So now we're talking about the market demand or the aggregate demand and the sub-market demand. So here, suppose that the demand function for movies is Q1 for college students and Q2 for other town residents. So what you might notice is that their x-intercept is the same, which is 120. So that's when the price is 0. So that's the quantity demanded when the price is 0. So they will at most consume 120 movie tickets, I guess. But you can see that the coefficients of the price is different for different group of people. For college students, coefficient is -1, but for other town residents, it's 0.5. So what does it mean? It means that college students are more sensitive to the price. So a higher price will affect the college students' demand negatively more than other town residents. So how to aggregate those two different demands? So basically, we just sum up the Qs. So the aggregate demand will just be a sum of the quantity demanded. But you have to be very careful about the range for the price. So for college students, the highest price that they can accept is 120, right? So when the price is higher than 120, they will not demand any movie tickets at all. But for town residents, the highest price that they can accept is actually 240, okay? So when the price is lower than 240, there is still demand, okay, among the other town residents. Maybe they have, a higher purchasing, not purchasing power, but they have higher savings or they have more money in their pockets to buy. Okay, so we have to be careful about the price range first, or aggregating those demand. And then we can kind of draw the graphs. So let's do the math first. So if the price is between 0 and 120, you can simply sum up Q1 and Q2. So Q is equal to Q1 plus Q2. So use the two formulas here, 120 minus P plus 120 minus 0.5 P. You will get 240 minus 1.5 P, right? But then when the price is above 120, so essentially Q1 is going to be 0. So it's going to be 0 plus 120 minus 0.5 P. So you are getting just 120 minus 0.5 P because when the price is above 120, the demand is totally from the out-of-town residents, not from college students at all. So you can see that this is a piecewise function, okay? The total demand function will be a piecewise function. So for the graphs, so this is a demand curve for college students. This is the demand curve for other town residents. So the demand curve for other town residents is higher and steeper. And then when you sum them up horizontally, okay, you'll see that there is a kink. So I think it's better to actually draw them together. So this red demand curve is the demand curve for college students. This green demand curve is the demand curve for other residents. And when you sum them up horizontally, you can see that when the price is above 120, it's just the green line, right? So the blue line, which is the total demand curve, coincides with the green line. And then after that, okay, it's actually higher than the green line because now you add in the demand from college students. So that would be excess 1.4. So just be careful. So the key takeaway from this question is be careful about the range of the variables, okay? All right, so one of the important questions that I want to spend more time with is actually exercise 3.3. All right, so here we are going to talk about demand and supply functions with constant elasticity. So what is constant elasticity? So first of all, you need to know what is elasticity. So the professor already talked about the elasticity of demand and elasticity of supply, right? So here you can see that the demand function looks slightly different from what we've seen before. So here we have the natural log. So I'm going to actually use my iPad to do some calculations with you. So here, can you see my iPad?
Yeah, we can see your iPad.
Okay, great. So let's use this exercise as an example to get familiar with the techniques that you need to know to be able to calculate the elasticity for this type of demand function. So the demand function is natural log of Q equals 2.6 minus 0.2 natural log of P plus 0.15 natural log of PT. And actually the PT is, I guess it's the price of the tomato sauce, I guess. And we're talking about the demand for processing tomato, right? Let's go back to the question and see what they are. PT is the price of tomato paste. Okay, tomato paste. So they are, so by looking at the equation, you can instantly know that they are kind of like substitutes, right? Why are they substitutes? So you can see that when the price of tomato paste is higher, you end up buying more processing tomato. Okay, you will substitute toward the other good. That's exactly the definition of, you know, one of the important feature of substitutes. And so we don't really want to focus on the other variables, right? So we just want to focus on Q and P. So here we found out that the price of tomato paste is 110. at that moment. So we just plug in their values, but we don't really care the value. So we don't need to, we can leave it and say it's constant. So then we want to calculate the elasticity of this demand function. So how to do that? So actually the formula for the elasticity is actually the partial derivative of Q with respect to P times P over Q. So that's the formula, but it's equivalent to this formula. It's the partial derivative of log Q with respect to log P. And why is that? I would like to actually show you why this is the case. So first of all, let's recall what's the derivative of log Q with respect to Q. Can anyone tell me?
dq over q.
So it's just the derivative of log Q with respect to Q. So it's actually,
Q.
What is that?
1 over Q.
That's right. So it's 1 over Q. So we will have 1, all right, it's too large. 1 over Q.
Wait,
And then,
what if it's like if it's ln x cubed, isn't that 3x squared over x cubed?
ln what? Sorry.
Ln x cubed, what's the derivative of that again? Is it just 1 over x cubed?
Yeah, if it is log x cubed over partial Q, I mean, what is, so are you talking about this? The partial derivative of log x cubed? Are you talking about this?
Oh, right, and x to the power of 3.
Oh, x to the power of 3.
Yeah, don't you have to still do the derivative in the numerator?
So actually, if it is x to the power of 3, okay, with respect to, with respect to x. So what is this? So before doing this, you can actually take down the exponent, take it out of the natural log, so that it will become 3 times log of x, okay? And then this 3 is just, you know, a scaling factor. So you will get, what you will get? You will get 3 over x.
And that's because in the denominator does it just become 1 if you take the derivative of just x?
So the formula for the derivative of log x with respect to x is just 1 over x, okay? That's just the formula. So you can also use chain rule here. So if you use the chain rule, okay, because here is a functional function. Inside the log is x to the power of 3. That's another function. So by applying the formula, okay, you will get 1 over x to the power of 3. But then you have to apply the chain rule, okay? You have to multiply it by the derivative of x to the power of 3 with respect to x. And then what you will get is 1 over x to the power of 3 times 3 times x to the power of 2, x squared. So you will still get 3 over x. So either way, just make sure that you're familiar with the derivative of a natural log, and then you're familiar with chain rules and other rules that I talked about last time, okay? All right, so let me move on. So similarly, we will get the partial derivative of log p with respect to p, and then it will be equal to 1 over p.
A question.
Okay, please ask.
How do you know that tomato paste and the tomato were substitutes?
Okay. By looking at the equation, you can see that when the price of tomato paste is higher, you buy more processing tomato, right? So, which means when the price of tomato paste is higher, you buy less tomato paste, and then you substitute toward processing tomato. So that's the idea of substitutes, right? When something else is more expensive, you buy the substitutes. Is it clear?
Yeah. Is it just because like there's a plus sign before the hit
Yes.
and then
Yes.
negative sign? So you know because of that. Okay. Thank you.
Okay. Let me proceed with the derivation. So now we know that the derivative of log Q with respect to Q is 1 over Q. Derivative of log P with respect to P is 1 over P. We can do a simple rearrangement. Okay, we can actually move the denominator to the right hand side. Okay, and then just divide the partial log Q by the partial log P, and then you will get. So let's do this. Actually, let me move this around. So move the whole thing around. Okay, I move it to here. And then let me erase the underline. Just divide each side. Okay, and then you will get this formula. So we have two different expressions of the formula of the elasticity. So you will have to decide which one to use depending on which one is easier to calculate. So by looking at this equation, you can see that the Q and P are in terms of their natural log. So we would like to use the left-hand side, okay, here. We would like to just take the derivative of log Q with respect to log P. We just treat log Q as something and log P as another thing. And then we take derivative of the function with respect to the variable. And then we instantly get negative 0.2. So by doing this, you will get negative 0.2. And then this will be the elasticity of demand for this demand function. And it's a constant, right? It's not changing. It does not change with the value of Q or P. So we call it a demand function with constant elasticity. And because the absolute value of this elasticity is smaller than 1, so we call this demand inelastic demand. All right, so if it is above 1, I mean absolute value, then we call it elastic demand. And if it is 1, then it's unitary elastic. So we can also transform this demand equation a little bit. So this is the form given by, I think, the textbook. You can see that there is this, exponential form. So how to get that? Actually, you just make the left-hand side and right-hand side exponents of the mathematical number e. So previously, we have log Q equals 2.6 minus 0.2 log P plus 0.15 log PT. But now, just add the E, okay, as the base. And then what we can do next is to do some rearrangement. We can actually decompose this whole thing into, different parts and multiply them. And then we can rearrange them. Let's put the last part and the first part together because they are constant values. So we can treat it, we can actually replace it by a constant A. And then we are left with this term in the middle. So let's put the negative 0.2 back into the natural log, and then it becomes the exponent of P. And then the E to the power of log of something is just that something. So we get a constant times P to the power of negative 0.2. So if you ever see, a demand function with this form, so actually we don't have the negative sign here. If you ever see this form, okay, Q equals A times P to the power of something. Okay, if it is a demand function, then you will instantly know that it's a demand function with constant elasticity, and the elasticity of demand is just epsilon. So it's just this number, the exponent of P. So we do this rearrangement and we see that the exponent is negative 0.2. And we calculate the elasticity, which is negative 0.2. So when you see this form,
could you explain how you calculate the elasticity above again? Like, I understand the constant elasticity function. Could you explain how you got negative 0.2 with the derivatives again?
Oh, you mean how to get the formula or how to calculate negative 0.2?
Oh, no, I understand the formula. I'm just confused. Oh, how did you get negative 0.2?
Oh, okay. So when you take the derivative, so let me use highlight to show you. I use green color. So this is the left-hand side, right? So this is the, I would say the function that you want to take the derivative of. And then this function is a function of log P. So you take the derivative of this function with respect to this variable, I would say. You treat the log P as a whole variable, okay? And then when you take the derivative, so you can just use, the power rule. The power is just 1. So when you subtract 1 from the exponent, it's just log P to the power of 0, and it's just 1. So you're left with just the coefficient before that variable, which is negative 0.2. So it's fairly straightforward. You can just treat it, okay, let me actually replace them by another variable. Let's just treat log of Q as Y, and then treat this as X. So you are essentially taking the derivative of Y with respect to X. And of course, you get negative 0.2, right?
Okay, so when we're saying dq over dp times p over q, that's essentially just taking the derivative of q or derivative of y with respect to x. Okay.
No, I mean, when you take derivative of q with respect to, you have to get an expression for q. Currently, you don't have an expression for q. You have an expression for log q. To get an expression for q, you do this procedure. You get an expression for q, and it's a times p to the power of negative 0.2. So when you take the derivative of q, okay, we can actually do this. We can use this new function to calculate elasticity as well. So just derivative of q with respect to p times p over q, right? And then, so for this part, derivative of q with respect to p, use the power rule. So I would say this part is equal to a times p to the power of negative 0.2 minus 1. But you take down the exponent, so it's negative 0.2. But then what is q? Okay, so you have, so this q is actually equal to a times p of negative 0.2, all right? And then, okay, so you can cancel this p with this negative 1. And then you can cancel the A with this A. You can cancel the P to the power of negative 0.2 with this. And then you are left with just negative 0.2. So you can clearly see that the calculation is much more complicated. You have to rearrange the equation to get an expression for Q, and then you apply this formula. So why not just take a derivative of natural log of Q with respect to natural log of P, right? So it depends on how the equation is written, and then you use the formula that makes the calculation easier. All right. So this is about the demand and supply. Sorry, I still have to talk about the supply. So similarly for the supply function, so in that specific exercise, the supply function is log Q equals 0.2 plus 0.55 log P. So now we can see that the coefficient of log P is just the elasticity, right? So the elasticity of supply is 0.55. And then we can do, transformation. Then we have Q equals B times P to the power of eta. So that eta is the elasticity of supply. So the demand function and supply functions with constant elasticity can be written as, a log, natural log function, or it can be written as an exponential function. So depending on how the equation is written, you will be able to use the formula that makes the calculation the easiest. All right, so let's move on. So this question also asks you to get I think this question is only about the equilibrium, right? So for the equilibrium, just equates the log Q, and then you'll be able to get this point. Equilibrium is when quantity demanded equals quantity supplied. Just equate the two quantities so that you equate the two natural log of the quantities, and then you can use your calculator to do the calculation. And okay, so for a linear demand equation, okay, so now we don't see any natural log. How to show, okay. So for this demand equation, it's totally linear, and then you have some values of the other variables, just plug those values in. And actually, we don't need to plug them in because we can just treat them as constant, and when we take the derivative, we ignore those variables. So what's the cross-price elasticities? So for cross-price elasticity and elasticity, so let's just calculate the price elasticity of demand first. So just apply the formula. We have an expression for Q, and the derivative of Q with respect to P is just the coefficient before P, which is negative 9.5. And then we know the value of P, we know the value of Q. Just plug in the values of P and Q to get the elasticity. And for the cross-price elasticity, the formula is, now you are interested in how the quantity demanded for sorry, we have one more people joining. I have to manually click the accept button. So the Q is the quantity of coconut oil, and PB is palm oil. So you are interested in how quantity demanded for coconut oil will respond to the price of the palm oil, so that you now calculate this cross-price elasticity to see how quantity demanded of one good respond to the price of the other good. And then we have the expression for Q, right? It's also a function of PP, and then you get 16.2. So they're substitutes because the coefficient is positive. And then you plug in the values of PB and the Q to get elasticity. So it's just applying a formula. Once you know what's the formula for elasticity, you should be able to do the calculation. So the only thing that you should pay attention to is what is the demand equation. Is it just a linear equation, or is it a demand function with constant elasticity? So with constant elasticity, there is a trick. You can just take derivative of natural log with respect to natural log of p.
Wait, question. Sorry, we kind of went over that last part really quickly. So the cross price elasticity is just taking the derivative with respect to the price of the other good.
Yes.
Did we have to take the price elasticity of demand for coconut oil as well? Oh, just say that in the question. It's just asking for both.
Yeah. That's the question. Yeah, the question asks you to calculate the price elasticity and cross price elasticity.
Yeah, but the cross price elasticity, you don't need the price of the main good. It's just the other one. That makes sense.
Independent. You can calculate one of them.
Thank you.
By themselves. Okay, let's move on to the next question. So this is not an important question that I would like to talk about today, but still we will go over this question. So basically it's asking you to prove a statement. So the statement is, okay, the less elastic the demand curve, an increase in a specific sales tax T reduces the quantity less. Okay, so now what's quantity? So quantity is a function of P, right? And here you should also know that the price will be affected by the tax. So now P is a function of the tax T. So really, this quantity is a function of function. When you want to see the effect of the tax, okay, on the quantity, you have to use the chain rule. So that's the key. So to prove this statement, just take the derivative of the quantity. That's part of the statement, right? You want to see how quantity change. Then with respect to T, that's the the cost of the change of the quantity. So when you take the derivative, just use the chain rule. So now it becomes dq over dp times dp over dt. So that's just chain rule. But then we want to relate this to elasticity. So recall that elasticity is dq over dp times p over q, but we don't have p over q here. Let's just add p over q and then add q over p so that we're not adding anything. It's like we're not adding anything. By doing so, we can actually extract the epsilon from this expression. So now we have epsilon times q over p times dp over dt. So now let's relate this expression with the statement. So the less elastic the demand curve. So by saying less elastic, it means that the absolute value of epsilon is smaller. Okay, but epsilon should be negative according to the law of demand. But we really just care about, the absolute value. But because epsilon is negative, so dq over dt is negative. So it's a decrease, okay? So the quantity will be reduced by the tax, okay? But when epsilon is smaller in absolute value, okay, the reduction will be less. So that's what this second part of the statement is saying. An increase in a specific sales tax reduces quantity less when, the demand curve is less elastic. So that's how we prove a statement using some mathematical equation and relate the the equation to the statement. So that's all for this question, I guess. So I guess this one is trying to familiarize you with calculus and the formula of elasticity as well. So the last one is a conceptual question. It's about the direction. So sooner after the United States reviewed the discovery of a single case of mad cow disease, in December 2003, more than 40 countries slapped an embargo on US beef. In addition, some US consumers stopped eating beef. So when 40 countries slapped an embargo on US beef, into the domestic supply. Yeah, so when there is an embargo on US beef, which means the US firms cannot export their beefs to other countries, what will happen to domestic supply?
It'll increase.
Yes, because you cannot sell your products in other countries, then you have to sell them in your own country, right? So now the supply to the domestic market will increase actually, but because of the potential health risk of eating the beef, okay, the domestic demand will decrease. So now we know that the supply curve will move up while demand curve will move down, right? Then we can kind of draw the graphs. But then the eventual effect is that the quantity sold increased by 43%, and the price fell by about 15%. So the final effect is that the equilibrium quantity is higher, but the equilibrium price is lower. So to show that, we have to make sure that the increase in supply is stronger than the decrease in demand, so that it will push the equilibrium quantity to the right. So the equilibrium quantity will be higher than before. Okay, but both movements will lower the price, right? So when the demand curve moves down or when the supply curve moves to the right, so I think I said move up. Actually, it should be moved to the right and move to the left. So when the supply increases, the supply curve moves to the right, not moving up, okay? So both movements will lower the equilibrium price. So you will definitely get a lower price, but to get a higher equilibrium quantity, you have to move the supply curve a little bit more. So that would be the first CA note. So I have a few questions in this note as well. But I won't talk about this one like too much, because the professor already did an example in his lecture recording. So this is about imposing sales tax, collect the sales tax from producers and see what's the final effect, what's the new equilibrium price with the tax, and then what's the deadweight loss, what's the tax revenue. So we can just look at this graph. So previously, without imposing the tax, the supply curve is P equals 10 plus 2Q. Demand curve is P equals 100 minus 4Q, right? You can calculate the equilibrium. But then with the sales tax, if you collect $18 per unit, then basically you move the supply curve up by 18, okay? So then using these two equations to get a new equilibrium with the tax. And then the tax revenue is, so the new equilibrium quantity is 12. And for each unit, you collect 18, right? So the tax revenue will be 18 times 12. And the deadweight loss is just this orange triangle. So you just use the formula for triangle. It's 1/2 times the base. The base is 18. And the height is just the difference of the two quantities. It's 15 minus 12. So the height is 3. So you get a deadweight loss. So that's what the professor did in his lecture recording. But today I would like to talk about another way, which is by making use of the marginal analysis. So I will actually show you on my iPad. So we don't have a lot of time. So I will just actually briefly talk about this and share this with you after class, and you can take a look. So basically, we want to use calculus to do the analysis. So first of all, we need an equilibrium. So the equilibrium with the sales tax or per unit tax can be expressed as this. So the left-hand side is quantity demanded, right-hand side is quantity supplied, but you have to figure out what's the price is. So let's say P is the price paid by the consumer. Then what's the price received by producers? So the producers have to send the tax to the government, right? So the price received by producers is actually P tau minus tau. So that's how much producers receive. So with this equation, we can actually derive the tax incidence. The tax incidence will be how the price will change, how the price paid by consumers will change with respect to tau. So we just take the derivative of both sides with respect to tau and then do some rearrangements. So if you take the derivative with respect to tau, so for the left-hand side, just use the chain rule. So it's dd over dp times dp over d tau. And the right-hand side, for the right-hand side, you still use the chain rule, but you have to know that the partial q or partial s with respect to partial p minus tau is actually equal to partial s with respect to just p instead of p minus tau. And I have an example here, and you can take a look later, so that we can simplify our equation to this. And after doing this, you can kind of rearrange this final equation to get an expression for dp over d tau. So this is actually in the textbook as well. So you can actually check the derivation in the textbook. And I will not spend more time with the derivation, but I will tell you why dp over d tau is the tax incidence on consumers. Because the P is the price paid by consumers, right? And this equation is telling us how much the price will increase for consumers from the perspective of consumers when there's sales tax, right? So that's exactly the effect of the tax on consumers. And it's definitely, so in most of the cases, definitely not one, right? So consumers do not have to share all the burden from the tax. The consumers share part of the burden, and that will be the tax incidence on consumers. We can express it as, you know, in terms of the, you know, elasticities. So elasticities of supply is eta, elasticity of demand is epsilon. So we can actually just multiply P over Q everywhere and then get the elasticities, right? And then we have this form. So we can actually use this formula to calculate the tax incidence on consumers by calculating the elasticity first. So sometimes it's easier to calculate elasticity, right? So you just calculate elasticity and apply this formula, and then you get tax incidence on consumers. And the tax incidence on sellers will just be 1 minus that expression. And then you get this. I think it's about time. So I guess I can talk about Lagrangian method today. So I will leave Lagrangian method to next week. It's actually kind of useful for chapter 3 only, not for chapter 2. So now today we are done with chapter 2. Do you have any questions that you want to ask before you leave?
Yeah, I have a, oh, you can go.
You can go.
Go ahead, Malika.
Oh, I had a question on 5.8.
5.8. Let me go back to 5.8. Yeah, so this is kind of like a quick Q&A after class. So if you have something to do, you can just feel free to leave. And if you have questions, just say, ask. I will ask Malika's question. So it's about 5.8.
Yeah, it was about the cross price elasticity. And is it because you were only taking DQ over the price of palm oil because the original equation was the demand of coconut oil? Because isn't cross price elasticity the change of quantity of the good 1 over the change of price in good 2?
Yes. So Q is actually the quantity demanded for good 1 is for the coconut oil, and the good 2 is palm oil. So this is the price of good 2. So P sub P is P2, and Q here is Q1.
Okay, so that's okay. Thank you so much.
Yeah, I have a question just regarding the showing our work on the exam. Are we allowed to write like on an iPad and then submit our work?
You can do like what I do here. You can use iPad. You can actually use iPad, and it will be actually easier for you to make a PDF, right? So just you can even type if you want, but I don't think typing is a good idea for this type of exam. Yeah.
Okay, thank you.
You're welcome.
Oh, I had a question. So for the tomato question, tomato and tomato paste, the answer you got was negative 0.2. And then I understand why you got negative 0.2, but I don't really get all of the work that you showed.
Oh, you mean how to get this?
No, for the tomato question, tomato.
Oh, tomato question. 3.3?
Yeah.
I think so. Which one?
It was like the partial derivative of the equation with respect to, partial derivative of ln q with respect to partial derivative ln p, and then the answer is negative 0.2.
Oh, okay. Let's just go back to my iPad again. So basically, you are treating log q as a variable and log p as a variable instead of treating q as a variable, okay? So now just treat log q as y and treat log p as x. So basically, you're taking the derivative of y with respect to x, right?
Yeah, I get that part. I just don't really understand like where the arrow is, that whole thing by the arrows.
You mean, sorry, what? Which?
It says partial derivative ln q with respect to partial derivative ln p is equal to 1 divided by q.
Oh, okay. So you're not quite sure about why this formula is this, right? So you want to understand this formula? This one? Okay, so basically it starts from understanding that the d of log q with respect to q, okay, is 1 over q. And then you just move the dq to the right-hand side so that you get this d ln q equals 1 over q times dq. And similarly, for d log p, you will get 1 over p times dp, all right? And then just divide d log q by d log p, and then you will get this 1 over q times dq over 1 over p times dp. And then this 1 over q divided by 1 over p is actually just p over q. And then you also have this dq over dp. So that's how you get this formula.
Okay, but you could also just go into the whole formula, like you have the green over there, and you could just, because that's how
that's right. Sense. But if you go over this one, you don't have q in this expression, right? You only have log q. So you have to convert the q you have to convert the equation to a function for Q. Okay, so now you have this whole thing here. So Q is equal to a constant times P to the power of negative 0.2. And with this expression, you can just use dq over dp times p over q. But then you can see that the calculation is more complicated.
Oh, okay, I see. Thank you.
Okay, you're welcome. Any other questions?
Yeah, actually, I had a question about the last thing you did in the chapter 3, talking about the elasticities using calculus.
Oh, you mean 6.8?
No, in the TA session for the using the deadweight loss and calculating.
Okay, you mean how to calculate tax incidence using calculus, right? So this is like our derivation. So we want to get dp over d tau, and that would be the tax incidence on consumers. You mean how to get this? Or I'm sorry, what's the question again? Which part?
You went about it, because I think you kind of went over it a little quick, but
okay, yeah, I can do it slower. So here we can actually just take a look at this. I think they have enough steps here. So basically you have quantity demanded equals quantity supplied, right? So I'm missing a partial D before S here. I will add that later. So the price here, we model it as the price paid by consumers. So the P is how much you pay, okay, as a consumer. So as a producer, because the government collect tax from producers, right? So I don't get P paid by the consumer. I get P minus tau, because every time consumer pay, the government actually extract the tau from the price. So I only get P minus tau. So that will be the price received by the producers, so that the quantity supply will just be, okay, plugging in that price, that value into the supply function, and quantity demanded will be plugging in the price paid by consumers into the demand function. So you equate these two. But after equating these two, you get equilibrium, right? We call it shocking the equilibrium. So then, based on that equilibrium, we can, take some derivative to get the dp over d tau. We want to see how the equilibrium price paid by consumers will change in response to the tax. So you take derivative of both sides with respect to tau, and then you will get this. Use the chain rule, so the left-hand side. When you take the derivative of d with respect to tau, so tau is actually a function, actually P is a function of tau, and D is a function of P. So it's a functional function. You use the chain rule, so you get d over dP times dP over d tau. So that's the left-hand side. And for the right-hand side, it's slightly complicated because inside the parentheses is P minus tau. But you should know that tau is part of the price. Tau is actually also a price, right? So when you take derivative of S with respect to the function inside, it's equivalent to taking the derivative with respect to just the P. Okay, I actually use an example to show you why this is the case. So for this example, so if P is equal to 10 plus 2Q plus tau, you can get Q equals P minus tau minus 10 over 2. Then when you take the derivative of Q with respect to P, you get 1/2. When you take derivative of Q with respect to P minus tau, you also get 1/2, right? So it doesn't matter if you are taking the derivative with respect to P or P minus tau. We want to simplify our equation so that we don't want to write P minus tau in the denominator. So, and then using the chain rule, right? The derivative of the function outside with respect to function inside is ds over dp. And then you also need to take the derivative of the function inside, which is p tau minus tau with respect to tau.
Mm-hmm.
So you do that, have terms. First term is p, the second term is negative tau. So when you take derivative of p with respect to tau, it's dp over d tau. And for the second term, you get -1. So that's how you get this part. It's chain rule, right? It's just that this is the derivative of the function inside with respect to tau. And this is the derivative function outside s with respect to p. All right, so now you rearrange this equation. You can break the parentheses. You can actually move the second term, which is ds over dp, to the left-hand side, and then you can move the original left-hand side to the right-hand side. And then you factor out the dp over d tau. Okay, so it's just simple rearrangement. And then you get this. The reason why we want to get this is we want to get dp over d tau.
Mm-hmm.
So you just divide this on both sides. So dp over d tau will be this term divided by this term, right? So now you have a formula. So this formula is, I think it's enough. So ds over dp over ds over dp minus d over dp. So you can actually, once you have the supply function and demand function, you can calculate the derivatives. But you can also calculate the elasticity, right? You can multiply p over q.
Mm-hmm.
You can multiply every term by p over q. And then actually they can cancel out, right? So it's the same. But by doing so, you get elasticity, right? By adding this term, you make the equation more complicated, but you are getting the elasticity. So if you know the elasticity already, just plug in the values of the elasticity to get the tax incidence right away, right? So that will be one way to do it. But for linear equation, getting the elasticity is actually more complicated. So you don't really need to use, calculus to do this question. You can still use what the professor did to do the calculation to get the tax incidence. It's okay. It's just like, I want to actually talk about 2.4 and 2.6, and this is kind of related to that two sections in the textbook.
Yeah, actually, if you don't mind me asking,
Mm-hmm.
this whole, I understand the purpose of this equation,
Mm-hmm.
and I understand the beginning and the purpose of the end, like how you're supposed to apply it. I just find the minutiae of getting from point A to point B to be kind of difficult for me.
Yeah, I mean, the derivation is not really,
it's just hard to, the notation is difficult for me to look at. But what the important part is that when we're taking something like the test or whatever, would we really only need to know the results, the end, like the last thing you showed us on the previous slide? Yeah, we don't have to prove it, do we?
For this particular one, you just need to know the final conclusion.
Yep. Okay. That's what I was concerned about, because I understand this. All of this slide makes sense, but the one that we were just on, which was the proof, that I just, like, if you told me to sit me down and do that myself,
the proof can be difficult for some people, and actually for most of the first learner, it's kind of difficult. But we don't expect you to fully comprehend that derivation procedure. Just know that there is a way to get to the final conclusion is enough. And then when you enter 400, I think it will be more about proof. But right now, it's more about application. So just know this formula. And when you are asked to do this, you just know which formula to use.
All right. Thank you. Thanks for the meeting.
All right. So I guess we have to end now. Otherwise, it will be too long. Okay. So I will end this meeting, and then so that people who can't attend will be able to watch the recording. Okay. So if you have questions, just send me emails anytime if you want, and I will try my best to respond. Okay. So see you guys next week.
Goodbye.
Bye.